Okay, let's review Euler's method. So we said the basic idea was that it uses numerical methods to get approximate solutions to differential equations given an initial value. So we're going to be looking at IVP or initial value problems. So it's going to be using tangent lines on small intervals to approximate curves, and as delta x or h little steps are taken, moving to the right or to the left, continuously corrections are made. So for example, we'll be given a differential equation you'll see that the function on the right side will depend possibly on x and y, describing the tangent lines of that curve for any given point x, y. And if we're given an initial location, let's say x0 and y0, and we want to get to the next step, we're going to be using a tangent line. So if I draw a little tangent line through x0, y0, and then look at this little triangle, and let's say my step size or h is right here, delta x, that'll give me a little change in y here, delta y. So from x0, I've taken a delta x or h step to the right and landed at x1, and I've also been able to approximate somewhere under my curve near it where my y value would be, and that y value I'm calling y1, which is this approximate y1, not the actual y value of the curve. Now another thing to notice is that this tangent line I'm looking at, we know this to be this guy, because that's what the slope is at that point. So that's just going to be f of x0, y0, because it's the slope of the tangent line through that point x0, y0. So I know that this little delta y over delta x is approximately really this slope that I'm going to get if I simply put in x0, y0 into my differential equation. And multiplying both sides by delta x, I get that delta x, f of x0, y0, is approximately close to delta y. I also know that this distance right here is y0, because from x0 to get up to that point, I went y0 units up. I also know that this entire distance all the way across, if I go y1, is what I have from here to here. So how did I obtain y1 in terms of the previous y that I knew? I took y0 and I added delta y to it, and that gave me what approximately y1 is, which is, as you notice, an underestimate compared to where I really should be in the curve. So y1 is really just y0 plus this little delta y that I'm looking at, and we know y0 from the initial condition that was given to us, and we have delta y here in terms of some other business that also involves our initial condition given. So in this manner, if we continue, y2 will be this guy, but depending upon y1 and x1. y3 will be this guy, but it'll use that previous step iteratively. We keep doing the iterations and we keep using the previous steps values, and if we continue in such manner, we'll have y sub n, so at the nth stop, meaning let's say if you wanted to approximate y of, I don't know, 10, let's say we're here at 1 and you wanted to go all the way to 10, you would take these little tangent line steps to ultimately get to 10, and what your guess would be for the y value, it'll be an approximation, of course, and along the way, when you came, you will have gone through all these other successive y values, and you can connect those xy coordinates and get an idea of what this curve should really look like. Even though you may not know exactly what it is, you're doing an approximation using this method. So, Euler's method uses this where delta x, or h, is the step size, meaning what kind of leaps you're making to get from what x coordinate to the next x coordinate. So right up above here, if your delta x is 1, you're taking 1 steps to move over to approximate your curve. If your step size is 0.1 or 0.2, even better, because you're taking mini steps, and then you have shorter line segments that are approximating your curve and trying to stay closer to it. So ultimately, our goal is to be able to use this. We know where it came from. We're going to go do an example now. Okay, use Euler's method to approximate y of 3 for the differential equation given with step size 1. So a pretty big step size. We want to know, and also let's have an initial condition. So we'll say for the solution going through 0, 0. So this will be our x naught, y naught. That's where we start from. And Euler's method tells us to use this iteration to get each successive step. Keep in mind, this is really your f of xy. That tells you the slopes. So y1 involves all the business about y naught and x naught, which I must have. I must have an initial condition. So let's go plug those values in. So once I plug those in, my y naught was 0, delta x is 1 in this case. And the derivative at 0, 0 was plugged in here. I still get a 0. So I started at 0, 0, but now I've taken 1 step to the right, and I'm still at the y value of 0. So this was my x naught, y naught. This is my x1, y1. Now I'm ready to go get y2. So in order to get y2, it says go use the business for y1 and x1. I plug in y1 from the previous step that I got, my delta x, and my x1 and y1 into my differential equation to get the slope at that point, and that gives me 1. So my y2 is 1, but I had taken one other step to the right from where I was. Delta x is 1, so 1 plus 1 is 2. So I'm at the x coordinate 2 and the y coordinate 1. This is my x2, y2. And I'm almost there. I have to go approximate y of 3. So one more step and I'm going to get at y of 3. So once I use my y2 and x2 from the previous step, I get my y3 to spit out a 6. So now I'm at 3, 6. This is x3. This is y3. I was supposed to go to y value of 3. So it looks like y value of 3 is approximately 6 using Euler's method as a solution going through 0, 0. Now what does that really mean graphically? What did we just do? We said this has a particular solution that goes through 0, 0, and that particular solution happens to approximately, for this sort of big step size, contain these ordered pairs. So if I connect these ordered pairs, I'm going to get an approximate solution for that problem. So here's what happened. Here's an idea. I'm stopping x at 4, but really for our problem there, it's said to approximate y of 3, so that's how far I'm going to look. Here's a slope field of that differential equation. That should really be a y prime dy dx. Here's a slope field of it. What did we just do? We said start approximating the solution going through 0, 0 with a flat line, horizontal tangent line. Then make a correction when you get to 1, and that's going to give you this other line. But then when you take one other step, it's going to give you a line with even a steeper slope. And you connect all the lines, and it approximately gives you, you can see you're off, because if you were to actually do the curve, it looks like it goes maybe something like that through 0, 0. But you're getting an idea of, on the right side, how the curve is behaving. If you go to the left, so your delta x, if you go one step to the left this way and this way and this way, you would get line segments to connect the other side of the curve. And this is what Euler's method has spit out, which was what we showed earlier. This was your y naught, here's your y1, here's your y2, and here's your y3. So when we get to x equals 3, the y coordinate is 6. And all that's happening here is all these ordered pairs are being plotted and then connected with lines to get an approximate solution to the curve that goes through 0, 0, but we have to have a starting location and where are we really going and stopping at to see exactly what the y value will be. Now if I make the step size smaller, it's going to behave even better. Now let's look at the same problem with a step size of 0.2. So you're not taking these giant one-step leaps to approximate the curve. You're making much more iterations, and some of them are listed here using Euler's method. Of course, you don't want to do it by hand. You start at 0, 0. The next value you get is going to be 0 still. The next value you get with a step size of 0.2 is going to be 0.08. So you have many more y values, and you're slowly going up, and notice how much better this approximation is of the curve compared to the line segments we did earlier. And each iterative step, each time you iterate Euler's method, it spits out all these y values. And it looks like it stops at 4. We're missing that piece that we were looking at. Y of 3 would give you a better approximation of what y of 3 is versus the 6 that we got earlier.